So one thing that I saw come up in the unit test some students had a synthesis that involved placing an alcohol onto an aromatic ring. How do we do that? Their instinct, which is probably drawn from all of the OChem 1 reactions, is that alcohols often form through a reaction with water. So if I can add water and maybe some heat here, then I might be able to see a hydration reaction. It's not hydration. It's still substitution. Could you predict the byproduct of this reaction? Given that it's balanced, one aromatic ring to one molecule of water, what would be the byproduct if this worked?
Hydrogen.
Yeah, molecular hydrogen, H2. So you want to take an aromatic ring and water and somehow form H2. To form H2, you often need a negative hydrogen and a positive hydrogen. You need a hydrogen that holds a lone pair, and you need a hydrogen that is bonded to something more electronegative than itself, anything. That's how you can form molecular hydrogen. So what hydrogen here would be considered more negative? The hydrogen on water is partially positive because oxygen is stealing it, and the hydrogen on the aromatic ring is partially positive because the aromatic ring is pulling on it. The carbons are pulling on it. So there's really no good way to form H2 here. This is just a logical approach to it. There's no good way to do it. Another way that I saw was to maybe have a catalyst like an acid, because we know that those acids can help run reactions, but if it's a catalyst, it's still trying to kick off H2, still not easy to do. So how do we do it then? How do we get an alcohol onto an aromatic ring? It can't be done in one step. You have to first put a halogen, which is going to be either Br2 or Cl2 for our class, and then a metal bonded to 3 of those, so either iron 3 bromide or aluminum trichloride. And that gives you a good leaving group. Now can I use water? No, water is not a strong enough nucleophile. Instead, we need hydroxide. We need water's conjugate base. Sodium hydroxide is great. Hydroxide is just as great. So any synthesis where you see an alcohol, an ether, a nitrogen group, and an amine, you can start by assuming you need to have a halogen at that position first, and then you can add that electron donating group. These reactions are not gone just because the unit test is over. When do these reactions come up again? On your midterm exam, which is how far away? 2 weeks from tomorrow. Isn't that wild? We just started this semester. Your midterm exam is 2 weeks from tomorrow, which is pretty close to the halfway point through the semester. It's also going to show up again on the final. So the unit test is meant to direct your studying as you prepare for the midterm and the final exam. So what I encourage you guys to do is make another list of your EDGs and your EWGs, your electron donating and electron withdrawing groups, and your halogens. And maybe be more expansive than the lists that I gave you. For instance, I don't think that I gave you the idea that an ester is an electron donating group when the ester is connected to the aromatic ring by by the alcohol. And I don't think that I gave you that an ester is an electron withdrawing group when the ester is connected by the carbonyl to the aromatic ring. So be expansive, be comprehensive if you want to. Try and think of how every little functional group connected to the aromatic ring might play a role as electron donating or electron accepting. And then identify the reactions that you can use to place those electron donating groups onto the molecule. What reactions place those electron withdrawing groups onto the molecule? See what reactions allow you to form what groups. There might be some reactions that you feel a little bit more challenged by than others, but I think that would be a good exercise. Look at your common electron donating, electron withdrawing groups. Figure out what reaction is needed to actually place that onto the molecule. I think we said most electron withdrawing groups are added via EAS reactions. Most electron donating groups are added via NAS reactions, but there's always a little bit of overlap. You know, there were a few reactions with aromatic rings that I didn't get into, and I'm not going to get into them, but I do want you guys to know that there are possibilities. Aromatic rings are not alkenes, but their pi bonds can still be hydrogenated. It usually needs not just a transition metal catalyst, but it needs incredibly high pressure, and it can be hydrogenated all the way down to cyclohexane. There are other ways as well to partially hydrogenate the aromatic ring and give us a non-conjugated diene. There's one other reaction that kind of involves, I guess, benzylic positions. There is a way to reduce a nitro group to an amine group. We didn't cover that reduction reaction, but I think you can see why it would be a useful reaction during a synthesis. We can easily add a nitro group via EAS. Then we could use that nitro group as a meta-director, and then we could reduce the nitro group to an amine. And now we have a new orthopara-director. On your tests, your multi-step synthesis was testing how well you knew how to add meta-directors, how to add orthopara-directors when they were necessary. And I felt this one just kind of clutters a little bit more, so it wasn't one that I focused on. You won't see this one going forward, but I do want you guys to know that if you go in search of other materials, you're going to find reactions like these. I'm not trying to hide things from you. I'm not trying to suggest this is too hard for you. But I am narrowing in on reactions that I think are more useful or more relevant, reactions that are really going to apply throughout the rest of the semester. We're going to deal with carbonyls and alkanes throughout the rest of the semester, so I wanted you to see the Wolff-Kishner reduction. We're not going to deal all that much with amines throughout the rest of the semester, so I wasn't so worried about you having those. All right. Now, the reason this was a useful segue, in my opinion, although I kind of derailed it, is because we're moving into a chapter on alcohols and ethers. You guys might notice that the two sections are separated, alcohols and phenols, and then ethers and epoxides. There's not going to be much segregation between the two sections. They're really going to bleed into each other. There's a lot of overlap between their synthesis and their reactions. So if you guys are ready, we're going to get started. And we'll start by looking at alcohols. first I want to give some properties of alcohols. Just looking at their acid-base properties. A less substituted alcohol is considered a better acid. We can actually visualize this by induction. So here's our alcohol. Do you know what the conjugate base of an alcohol is called? Oxygen? No, not quite. We have to imply that it's negatively charged somehow. How do you imply that oxygen is negatively charged?
Anion.
Change the suffix to make it sound like an anion. How do you change the suffix to oxygen to make it sound like an anion? What is O2 minus called? What is the anion form of oxygen? Oxide. But this is not oxide. This is a negatively charged oxygen, not a 2 minus charged oxygen. And it's not just oxygen, it's bonded to an alkyl group. So what would you call it? An ALK for alkyl, alkoxide. So oxide indicating negatively charged oxygen, ALK at the front indicating it's also bonded to a carbon group. So which of these has better acidity? Which of these deprotonates to the largest extent? Which of these is the best acid?
Methoxide.
Well, methoxide isn't the alcohol, but methanol. Or sorry, yeah, methoxide's not an acid, but methanol is the best acid. Methoxide forms to the largest extent. Sorry?
So the alcohol is the one donating the electrons, right?
Actually, the alcohol is the one taking electrons away from hydrogen.
No, we're not. Like an aqueous solution reaction, that would be the donating electrons, right? That's what acids are, right?
No, acids are always electron pair acceptors. Yep. Bases are electron pair donors.
Okay.
And that is true from the most broadest level of acid base all the way down to the most narrow definition of acid base. Remember that there is Lewis acid base, which is the most encompassing, then Bronsted-Lowry, then Arrhenius acid base definitions. And in all of those, the base is using its lone pair to do something, and an acid takes electrons during the process. In the case of Bronsted-Lowry, there's always, in addition, there's always a hydrogen ion that is being transferred. So you can see here, I've created a negative charge. What's balancing that negative charge? Can't go from net neutral to net negative. In all of these instances, there is a loss of the hydrogen ion. Or maybe, in reality, there is a base that is bonding to H+, so a transfer of the hydrogen ion. Which of these bases along the bottom, then, is the strongest base? Which of these is the most willing to go to another species and take a hydrogen away from it? If the least substituted alcohol is the best acid, that means it forms the weakest base, the one that is worst at taking a hydrogen. So the most substituted alkoxide is the strongest base. Well, this might help explain why we use tert butoxide so much, but there is some difficulties that come with running tert butoxide, and that is its steric hindrance. It's so bulky that it can impede what regiochemistry you want. So we can say the more substituted alkoxide is the best base. And to be honest, the pKa range here is within an order of magnitude. These typically have a pKa character between, I guess, maybe 15 to 18, maybe a few orders of magnitude. That's, from 15 to 18, 3 orders of magnitude is actually 10 to the third power. So there's a range of 1,000 times better acidity or basicity. But that's comparing an alkoxide. Well, let's say comparing an alcohol as an acid to acetic acid. Acetic acid is still considered a weak acid. Acetic acid, a carboxylic acid, has a pKa around 5. That's 10 to the 10 times better of an acid. That's 10 million times better of an acid. Or in other words, alcohol is 10 million times worse of an acid than vinegar. So here, their range is very narrow. Technically, water is not an alcohol, but I like to think of water as inorganic alcohol. And it has a very similar pKa. Water's pKa is around 15.6. That's on the more acidic side of alcohols. And you can see water, not very substituted. Less substituted, better acid. But of course, when it comes to water compared to alcohols, you really change the game up a lot. There's twice as much hydrogen bonding in a molecule of water compared to an alcohol. And there's a lot less van der Waals forces. So it's not a perfect comparison. So this family here, pKa's between 15 and 18. How do you think this changes for a phenol? Is a phenol similar in acidity? More acidic? Less acidic? I didn't really explain it here, but the more acidic? You said the same thing, Caesar? Less acidic?
So,
I should have given us a little bit more background, but when we look at acidity, we can use Cario to help explain it. Which part of Cario explains this acidity trend?
What is Cario?
Sorry?
What is Cario?
Charge. Did I not go over this in our OCHEM 1 review? Sorry. I'll introduce it now.
yeah.
Charge, atom, resonance, induction, and orbital. And atom actually breaks down in 2 ways. We look at electronegativity if we're comparing 2 atoms that are in the same row. We compare size if 2 atoms are in the same family, in the same column. Resonance, induction, and orbital. We're not going to have to get into too much of those examples given the fact that all of these alcohols have the same charge and the same atom and the same resonance, which is 0, and they're all the same hybridization, they're all using the same orbital, there's really only one characteristic of karyo that helps explain the difference in acidity for these alcohols, and that is induction. Do any of you have a good idea of what induction is? Within chemistry or outside of?
I mean, within chemistry, it's kind of like when it's pulling electrons away or pushing electrons kind of towards it. So like in this case, it's kind of more giving that more of the negative charge because it's like pushing, it's like the solvation effect, whatever they called it.
Yes. Yeah, so induction is the idea of, and I'm glad you said both, it's a push and pull of electrons. Induction can happen in 2 different ways. You might think of induction with like an induction cooker. I think that's something that uses magnets to create an electrical current. Induction is also related to the word induce, like if you have induced labor, you're forcing something to happen. And in the case here, it's forcing electrons one way or the other.
I think with charge, like you said, magnets, but I think electrical currents are from induction.
So when you set it on a wireless charger, using magnets to create an electrical charge that charges your phone. Exactly. Here, what we're looking at is having more electron density behind your alcohol pushes onto that negatively charged oxygen, which essentially increases its magnetic behavior. It makes it a stronger magnet so that it goes out in search of a hydrogen ion more. Having less electron density behind that oxygen makes it a little bit of a weaker base, which means that its acid is a little bit of a better acid. So induction here explains the acidity of alcohols. Sorry?
So then that would be less acidic than the alcohol.
Than an alcohol? Because it's less substituted. It's not quite as substituted as tert butanol. It doesn't have this big sterically hindered carbon right behind it.
Wouldn't it be more acidic because the base is more stable because of resonance?
Good. So phenols are more acidic and the reason is resonance. Yep. That negative charge isn't just sitting on oxygen, is it? That negative charge is conjugated to the aromatic ring. And this looks very similar to what we saw in our, sorry, I drew my ring so badly I lost track of where it was. This looks very similar to what we saw in our aromatic substitution section. I'm going to kind of run out of space to draw the final resonance form. But there is one more after this. That's delocalized. That base is delocalized. Now there's still one atom that is most likely to use the electrons as a base, and that's the oxygen. Typically, carbon being less electronegative, if any resonance form puts the lone pair on carbon, carbon will use the lone pair. Carbon will act as a base. Carbon is a better base than oxygen. Oxygen is a better acid than carbon. But here, if any of these carbons uses the lone pair, it ruins aromaticity. So there's actually a preference for forming the aromatic ring if this conjugate base acts as a base, which means oxygen acts as the base. And what would happen if we added an electron withdrawing group to this structure? I'm going to draw two phenols. One of them is going to be ortho-nitrophenol, and one of them will be meta-nitrophenol. Do you think an electron withdrawing group changes the acid-base character of the phenol?
Makes it less acidic.
Makes it less acidic, makes it a stronger conjugate base.
Right.
Why?
Because it will pull on the electrons. They can't, so the hydrogens are more stable, I guess, more like they want to stay.
So this nitro group is pulling on electrons.
I'm sorry, that they want to leave.
They want to leave. The hydrogens want to leave more. I think that sounds like a better acid. I know this is why we're talking it out, right? Because you can logically work your way through this, but you've got to go through that struggle of, am I thinking of its acidic form or am I thinking of its basic form? And really you can think of it two ways. As an acid, that electron withdrawing group is pulling electrons towards itself, which means oxygen would be more willing to give away its hydrogen because it can take that excess negative charge and give it to the nitro group. But also, if I think of its conjugate base form, where is that negative charge going to be? The nitro group can help pull onto it and stabilize it. So electron withdrawing groups increase acidity. I know I'm being very generic here, and I'm just saying better acids. We could do some research and find compounds and look at their pKa's and list it. But I'm not going to have you guys look too much at pKa's. And I know I keep saying here, better acid, better acid, better acid. Well, it's a compounding effect. It just keeps getting better. And there's two reasons. This compound here has better acidity, a lower pKa, due only to induction. The idea that the electron withdrawing group helps pull some of that electron density towards itself. Actually, the exact opposite of this induction. Here, the methyl groups are pushing electron density to make it a better base. Here, the nitro group is pulling electron density to make it a weaker base, which in turn makes it a better acid. But this one is not just because of induction. There's a stronger effect here, which is resonance. Now, this bottom meta-substituted phenol, it has the same resonance, that's why I'm putting this in brackets. It has the same resonance as phenol. That lone pair goes to the positions ortho and para to the alcohol. And because of that, the lone pair can never truly be impacted by the nitro group. I'll put my little resonance arrows or resonance brackets up there too. But with this ortho or with a para-substituted group, I'm actually going to expand nitro. So we're going to say double bond, single bond, negative charge, positive charge. When my nitro group is ortho or para, then the lone pair from the oxygen can move directly into resonance with the nitro group. Lone pair forms a double bond with the carbon. Carbon-carbon double bond moves to a carbon-nitrogen double bond. Nitrogen-oxygen double bond breaks open. So that electron withdrawing group makes the acid more acidic due to induction and resonance stabilization when it's placed orthopara. Now here's an interesting question for you. Which of those two resonance forms is a major contributor? First, recognize that this conjugate base has additional resonance forms. It has all three of the resonance forms that you would have seen up here as well. It has resonance forms where the negative charge sits on the carbons that are orthopara. Those are not major resonance forms because it places a charge inappropriately. It puts a charge on a less electronegative atom when it could be placed on a more electronegative atom. These are the two most major resonance forms because the most electronegative atom holds the negative charge. Between them, could you try to offer which is a more major contributor?
Could it be the same?
They could be the same. What differences do you see that could affect how much they contribute to the molecule?
I guess the difference, I have a guess because of it, but like whether the negative is like closer to the phenol, because it's like the one on the left, the oxygen connected, or not the phenol, but
Yeah, the phenoxide.
okay, sure. I'm like the oxygen closer to it has the negative, whereas the other one, the oxygens that are like connected to the nitrogen have it.
So which one do you think is better? When the oxygen is further from the nitro, or when the negative charge is on the nitro?
I'm not sure, but I'm guessing that has something to do with it.
Okay, I do like that you pointed that out. What I'm seeing here is a cluster of charges. A negative, positive, negative. One rule about resonance that we don't talk much about is having opposite charges adjacent to each other is kind of a no-no in resonance forms. We see that a lot when, for instance, you take a carbonyl and you just pop the pi bond to the oxygen. You create a negative and a positive. Having adjacent charges is not ideal because adjacent charges usually means they can just stabilize each other. And here I've got a negative and a positive and a negative. I can really never overcome the negative and positive being next to each other. A nitro group always looks like that. But maybe I could minimize having that additional negative charge next to it. The other thing that I notice here is this resonance form emphasizes aromaticity. It keeps the aromatic ring in that aromatic bonding pattern. And this resonance form breaks aromaticity. It takes these pi bonds outside of the ring, kind of inhibits some of the conjugation. So what Rolf said was true. It might be hard to predict which of these is more major. They might be equal. But there are a couple of things that we could look at. How close are those charges to each other? And how well is the aromatic bonding pattern stabilized or emphasized? Okay. Let's try and apply this a little bit. I'm going to take a really strong base, hydride, which you're going to see show up this semester as sodium hydride. So I maybe should have just put in NaH. Notice that this compound has two aromatic alcohols, two alcohols attached to the aromatic ring, aryl alcohols, phenols. And it has an alcohol coming off of its acyl substituent. That's not a carboxylic acid. We would actually call it a beta hydroxy ketone because it's at this position 2 away from the ketone. This is a strong base, H minus, so it is happy to take electrons from, or sorry, happy to take a hydrogen from just about anything. Where is it going to go first? Which of these alcohols is the most acidic?
One of the rings. The ring.
Which one? Well, let's stop and see if you guys agree. Do you guys agree that one of these two alcohols will be more acidic than this?
Would be that top one.
Can you describe its position in the molecule? Would that help
The
you justify its acidity?
the para to whatever that is
We could call it generic.
Yeah, the electron dry group.
Right. So the alcohol that is located para to the electron withdrawing group on the ring is going to be the most acidic alcohol. I really feel like I'm going all over the place today. I apologize for that. We can actually give a better idea for the pKa of phenol. The pKa of phenol is about 10. So that's 5 orders of magnitude better than an alcohol, or 100,000 times more acidic, which means that these are going to be at a pKa less than 10. I don't want to get too much more specific than that because I don't have real numbers. But Caitlin's exactly right. The ring is going to stabilize the negative charge, which is why one of the phenols is more acidic. And the carbonyl group can help stabilize the negative charge of this para-substituted phenol. That's our most acidic position.
Should we know the pKa's?
No, that's actually why I hesitated to give them to you, because I'm not trying to encourage you to memorize pKa's. In my opinion, you can be very effective at predicting acidity without needing to gauge pKa values. But I do know that some people like pKa values. It gives them kind of a number to grab onto and gives them a gauge. So not a requirement, just if it's useful for you. All right, good application? Good. I do want to keep this in mind, the acidity of alcohols, because some of the reactions we're going to do this semester, we can't have alcohols present. If an alcohol is there, it will act as an acid, and that's very dangerous for us. Okay. We're going to take a quick detour from alcohols and look at a class of reagents called organometallics. Organometallics are going to be incredibly useful for us in synthesizing alcohols. Those of you that are in lab saw this in the experiment last week. You created an organometallic and used it to synthesize an alcohol. Organometallics, like the name implies, has a carbon to metal bond. One of the best advantages of a carbon to metal bond is the incredibly strong dipole moment that points towards the carbon. So in other words, organometallics are very strong bases and very good nucleophiles. Being that they are very good bases, we need to be careful how these organometallics come into our reactions if there are alcohols present, because alcohols are weak acids, and a very good base will take a proton from any type of acid. So we need to be very careful. We're going to look at 3 types of organometallics. 2 of them are very similar. In terms of writing them on paper, 2 of them are interchangeable. They will have the same effect throughout the semester. The third is distinct. It's a little bit more moderate. We can control its reactivity a little bit more. So first, we'll look at organolithiums. And we'll look at how to prepare these organolithiums. To start, we need an alkyl halide. Actually, all we need is an organohalide, which means R here can be an sp3 carbon, an sp2 carbon. It can be an aromatic ring bonded to a halogen. So we'll look at a few cases. Over the reaction arrow, we need 2 equivalences of lithium. Correct me if I'm wrong. Is that lithium? That's not, I'm not wrong. Here's a question. Is that lithium ion? Do you see a charge next to the lithium? Do you see a counter ion next to the lithium? Is it LiOH to indicate that it's lithium hydroxide, lithium ion? No, that is elemental lithium. If it helps you to remember that this is elemental, you can put the charge next to it. The charge is 0. And the product that we form is RLi. Notice, though, that our stoichiometry is not balanced. First of all, where is the halogen? And second of all, where is the second equivalence of lithium? So what is the byproduct that forms in synthesizing an organolithium reagent?
Actually, lithium today.
Right. So LiX is a byproduct. And look at the transformation that occurs. We go from having a partially positive carbon to having a partially negative carbon. And by partially negative, I actually want you guys to think of this as a full negative charge on carbon balanced by a lithium ion. Their bond behaves somewhat covalently. But if you look at the difference in electronegativity, it technically falls into the category that we call ionic. It also fits the definition of ionic, a metal and a nonmetal. So we'll draw it covalent. You are more than welcome to think of it as ionic. I don't encourage that about everything. For instance, this OH bond, that's covalent. Hard stop. Not ionic in any way. This covalent bond requires a lot of energy to break. Maybe less energy than most, but still requires the energy to break it. This ionic bond / covalent bond is very different. All right, let's do some examples. I'm leaving some things blank. So I want you guys to fill in the reagent for the first one, predict the product of the second one, and determine a starting material that could work for the third one. I'm going to make a slight change. I'm using bromine too much. I don't want you guys to think that bromine is the only way to get here, but bromine is one of the most common halogens we'll use throughout this semester, so I want you to recognize it. Great. Filling in the reagents, is that the easy part? Good, that's the product we're looking for. You got it, those all work. Perfect, yep. Good. You did it, good. Okay. Good start. That's right. Yep. So, organohalide to organolithium, I need 2 equivalences of lithium. This is a vinyl halide, 2 equivalences of lithium, a vinyl lithium. And here I have an alkyl lithium, which means I'm really just going to copy the same carbon chain, but attached to this primary carbon, I need to have any halogen. So I'm going to switch it up for you guys and give you iodine. And I think we could fill in all of the byproducts here too, correct? There's a byproduct of lithium bromide, a byproduct of lithium chloride, and a byproduct of lithium iodide. Now, some of you put bromine, some of you put chlorine. All of them are correct. I think the most challenging part of that last question was making sure that you didn't add any carbons or lose any carbons. So you could take advantage of something like mapping your carbons to make sure that no carbons were added, no carbons were lost. There's really no wrong way to map your carbons. Okay. We're not going to look at a mechanism for this reaction because it's really not presented anywhere, and it's challenging. Lithium here is being oxidized. How many valence electrons does lithium have to lose through oxidation? Sorry? I heard somebody say it. You said nothing? I'm hearing things. How many valence electrons does lithium have? What charge does it take on? Lithium likes to take on a +1 charge. Lithium is an alkali metal. So lithium has 1 electron to lose. What we're looking at here is a 2-electron reduction. This carbon goes from partially positive to partially negative. Essentially, it gains both of the electrons from the bond. So it needs a 2-electron reduction, which is why we need 2 equivalences of lithium. Each lithium gives 1 electron in the reduction process. Okay, that's organolithium. The next organometallic that we'll look at is organomagnesium halides. These go by another name. These are called Grignards. Spelt Grignard, pronounced Grignard. Not sure it is a person's name. I'm not sure the region of the world it comes from. I feel like French doesn't usually have a lot of G's in it, but the silent letters makes it sound more French. Somebody know? Does that look familiar? Anyways, named after a dead guy. So I like to call them organomagnesium halides, but that is really a lengthy name, which means I'm going to call them Grignards a lot. Obviously, you can see that the metal that's being used here is now magnesium. So we'll start with an organohalide again. We'll react magnesium, and what we get at the end is not quite the same as our organolithiums. The magnesium is shown to have a bond between carbon and the halogen. Once again, these are drawn covalently, but you should think of them as ionic. What's the charge on magnesium there? 2+ in the product. What's the charge on magnesium over the arrow? Neutral. This is elemental magnesium. So those of you in lab, you took those magnesium flakes and you ground it up and you dumped it into your reaction. You took metallic magnesium to run this reaction. So once again, you're welcome to put 0 there. A lot of places when you see this reaction, you're also going to see ether or ETO or THF. ET2O is diethyl ether. THF is tetrahydrofuran, which is also an ether. So by saying ether, you're saying any inert solvent. This is not something that I require of you to put. It's something that you might see, but it does tell you something about the chemistry. These reagents are incredibly reactive. They cannot just be run in any sort of solvent. You need an inert solvent. We don't focus all that much on solvents, though, in the lecture class. And it feels odd to me to say, when we run our acylation reaction, When we run our EAS reactions, our NAS reactions, we don't list a solvent, even though a solvent is necessary. But now when we run preparation of an organometallic, we need to list the solvent. I disagree. So I want you to be aware of it, not something that you're rated on. Let's do some examples. Okay, in the first one, I'm going to have a para-substituted Grignard, toluene Grignard. You might call this p-toluene Grignard. It explains the rest of the aromatic ring and explains that it's also a Grignard compound. Notice that the halogen sticks around. That's because we only have one equivalence of magnesium. Magnesium does the 2-electron reduction on its own, but that magnesium now needs to be balanced by the halogen as well. Reagents up here, Mg. If you want to put Mg in ether, it's not wrong. It's only more correct. And down below, what would be a good reagent to use? Can you give its IUPAC name? Bromobutane. I need a little bit more detail. 1-bromobutane. Or we could call it N-bromobutane. N for normal. 1-bromobutane, 1-chlorobutane. Oh no, sorry, 1-chlorobutane wouldn't work, would it? Because I've already given you that the product is a magnesium bromide Grignard. So we couldn't use 1-chlorobutane. We couldn't use 1-iodobutane. Now we're a little bit more limited, unlike we were here. I will say this is not the most common organometallic. In fact, this compound, butyl lithium, N-butyl lithium, is so well known or so well used, it's referred to as in-butyl. You just take that normal butane chain, attach a lithium at the end of it. This is used not so often as a nucleophile, but very often as an aggressive base. You create in-butyl if you need something that's hard to deprotonate. All right, here's a question for you guys. You step into the lab, you try to make this organometallic reagent, and you can't isolate it. The question is, why can't you isolate this product? Start with parachlorophenol. Add 2 equivalences of lithium. Try to create para-lithium phenol. Why can't you isolate it? And maybe I can clarify that you're not isolating this by saying on the reaction arrow, the ugliest reaction arrow you ever did see, a big X, which is to say you can attempt it, but you will not form this product. One way that you can try to answer this is to figure out what would you form instead. If that's not isolated, what is isolated? The starting material? A different compound?
It would be metal lithium from the OH.
So you're thinking that maybe you get this compound instead?
Yeah.
Caesar?
So the hydrogen would leave and the lithium would get touched the oxygen?
Okay, so you think that this compound would be isolated
With the
with the chlorine.
and then I think it's an acid.
It's an acid, but is this a base?
Well,
So that would turn it into that base, but then that's an acid and that's a base, and then wouldn't the H just go over to the
Are you suggesting that on this stiff aromatic ring, the lithium bends over and grabs the H? Or the carbon takes the electrons, rather? And
No, I guess not.
Well, earlier you said that these are very strong bases and that they can have alcohols because alcohol's a weak base
acids,
or
weak
weak
acids.
acid.
And a weak acid and a strong base, that's still going to run an acid-base reaction. Well, let's run with your idea. Maybe we're not quite sure how it would happen, but what product would form if this acid and this base reacted with each other?
Just be the negative oxygen.
With anything down here? No, if that's a base, that carbon then, actually maybe instead of circling lithium, what I should circle is the carbon is a base. The lithium is not a base. The lithium, remember, is basically a counter ion to this negatively charged carbon. If that's a base, that means it's going to accept hydrogen. If that's the acid, then this is the hydrogen being accepted. What would be balancing that negative charge? It wouldn't be nothing. This is net neutral. This should be net neutral. Resonance doesn't counterbalance a charge. What's the positive charge counterbalancing this anion? Carbon is now neutral. They suggested that carbon takes the hydrogen. So carbon is neutral. Where's the lithium? which we could actually write just like that. We could write OLI. It's almost the same as writing NaOH. You're bonding a metal and a non-metal. That's an ionic bond. So you can show it ionic, you can show it condensed. Okay, so I want to look at the options that we have. This first reaction, or this first predicted product, do you have a rationale behind it? Why does the lithium substitute a hydrogen, and what do we expect the byproduct would be? Looking back at your preparation, okay. Looking back at our preparation of the organohalides, what do we need every time in our starting material? We need a halogen leaving group. So this one, probably not our best option, because rather than reacting at the halogen position, it reacted at a hydrogen, and it would have produced LiH, which is not impossible to produce. Up here, earlier I gave you NaH, so we know that we can make H- bonded to a cation. The second one, again, we ignored the halogen. And again, the idea is, why can't we isolate it? So I'm glad that you guys were looking for other options. But it suggests then that the lithium is doing actually the same thing to this hydrogen that the lithium did to this hydrogen in this product. It's producing LiH-. So actually both of these share a byproduct of LiH-. But that's not the preferred place for this reaction to occur. What is going to happen, this forms. And then molecules that are next to each other, so not one molecule reacting with itself, but molecules in solution reacting with one another, react to give us this product, which I just want to emphasize again, can be written as OLI. And given that there's no other substituents on the ring, we can also abbreviate this as PHOLI.
Do you have hydrogen chloride as the byproduct or what?
Yes. No, not hydrogen chloride. Oh, well, actually, this produces a byproduct of lithium chloride. This first reaction produces a byproduct of lithium chloride. But the acid-base reaction doesn't have a byproduct. You'll notice that carbon bonds to the hydrogen, and the oxygen ionically bonds to the lithium. So the hydrogen is now at this carbon.
Is it a reaction that we have to know?
It's something we need to be very mindful of, because we're going into a section on alcohols, and we're also going into a section on carbonyls with organometallics. We're going into a section with organometallics and alcohols. We can't use them in the same reaction.
But I mean, is what we need to know that we should, if there's an alcohol, it's not going to happen, or do we need to know that if there is an alcohol, it's going to be OLI or ONG or NGO or whatever.
Not that it's not going to happen. The preparation of the organometallic did happen. We need to be mindful that I'll write this down so that we know it's important. If an organometallic forms with an alcohol, an acid-base reaction follows. The other reason I wanted to show this was to get you guys out of the mind frame of, sorry, is it just hard to read or is my handwriting bad? Some of you guys really glare at the screen. I want you guys to get out of this mind frame of thinking, I've got one molecule drawn on the board. That's the only molecule in existence. And I want to get you thinking about, this is supposing a reaction in real life. And I know some of you are in the lab and some of you are not in the lab, but you all have at least been in a lab setting before. You know what it's like to mix reagents together and swirl them. If you mix a millimole of this reagent, 0.001 moles of this reagent, which would probably weigh something like 1 gram. Do you know how many molecules of that reagent you have in solution? A millimole. 1/1000th of a mole. 6.022 times 10 to the 20th molecules. 600,000 billion molecules. A ton. So you're showing one representative reaction of billions of molecules. So I want you guys to keep that in mind. You show one product, that doesn't mean it's going to react with itself, although we are going to do a lot of intramolecular reactions. Oftentimes it means it's going to react with the molecules around it. So maybe I should have shown 2 molecules of this reacting together to form this byproduct. Okay, I want to give you guys a quick break. So why don't we take 5, get up, move around, get your blood flowing, and we're going to look at our 3rd class of organometallics.
Yeah. Wait. There you go, Adam. You are pretty good. 45. Yeah. That's pretty good.
Yeah. I had my daughter. Same questions.
What do you think was the hardest part?
Now looking back in there, it's like there's too much to read.
The passages require a lot of skill.
Yeah.
You have to know how to skim and pull out the most meaningful information.
Yeah.
Sometimes I don't actually know. There are people that like teach how to study for the MCAT, how to take the MCAT. But one thing that I would do, because I've looked at some of those passage type questions, a lot of times you get several questions on the same passage.
Yeah, that's how most of it is.
So what I would do is skim through the passage. Don't read every word. Get an idea of what it's talking about. What is the context? What are big words that you see in there? Then get down to the first question and see what the question is trying to ask. You might not know how to answer it because the information is embedded in the passage. But now you can go back up to the passage and read it a little bit more meaningfully. You can focus on parts that help you answer the question below. And then you do the same thing again. Go to the next question, see what the question is really focusing on, and find that in the passage.
There's a lot of biochem stuff.
Biochem stuff.
Most of it is biochem and biology. you were doing like physics, but the passage was based on something chemical. They would talk about the electrons, the physics of part of it, the electric part of it, physics of the whatever molecule you're looking at. That's crazy. It's not like this is just chemistry. This is just this knowledge that you can buy. It's crazy.
What practice course do you take?
It was the ANC. The first one is free.
Long as I take it.
5 hours and some minutes. Yeah, just like I said, someone had questions I just didn't know, so I just answered. Get your knowledge around.
I don't envy you guys.
It's a long test. But I thought it would be more like when I took a test like for college back in I think it was a South American bike, like kind of like SAT type. I came out and my head was hurting. It was on the way. This one was like it was chill, like I understand what it is, but it's long, but it didn't hurt my head.
Yeah,
So I don't know.
that's a good sign.
Yeah, like you can actually think through it if I knew some of the material.
I helped a friend study for the MCAT, going over the chemistry questions. It hurt my head. I was there for like 2 hours or 3, not 5 hours, and I didn't look at the physics questions, and I didn't deal with the biology questions. I looked at just the ones that had chemistry in them, and it hurt my head. But it did give me an awareness of what my students, most of my students, have to do. You know, one of the reasons I teach chemistry is because I have seen a lot of bad chemistry teachers. One, I like teaching, obviously, and I like chemistry. But I also wanted to, I had this mindset of, if I fill the role, somebody else won't. So it's either me or they get stuck with somebody who might not do as good of a job, someone who might not care quite as much. So I said, I want to do it. And then I realized I really had my work cut out for me because I can't just make it a fun time, you know, and like, let's just draw pictures all day and I'll give you guys 100%. I have to really set you up for success, which is challenging, and make it a fun time. So I feel like me going through MCAT study guide stuff made me realize the way that I spend time up here is really meaningful. It's impactful for your ability to do well on other exams coming later. Not just well on my exams, but well in material that is not like my exams. That's why sometimes I take a minute to say, here's other things that happen, because I want you guys to know that what we focus on is not comprehensive. Like the whole world of chemistry is so big.
I feel like too, like it's more like this where you have to like you get the basic knowledge of the charges and this and that, but it's more what it looks like it was more analysis than actually knowing straight up memorizing facts or anything like that.
Yeah.
You could actually like think through some of the questions and possibly get the answer by elimination. It's like a method to it.
Mm-hmm.
That's what we want to test you on, really, like how well will you be adapted to those problems and analytical thinking and stuff like that.
I think that I don't want you guys to walk out of this class memorizing stuff. I want you to walk out of this class knowing how to analyze things better. I want you to think about how charges behave, how charges are predictable. One of the reasons I don't teach the ozonolysis mechanism in my OChem 1 class is because it's not easily predictable. It doesn't make a lot of sense. All of the other reactions are very meaningful. If you can gain the intuition of how to follow charges, you can solve almost any reaction. So like Ralph asked earlier, do we have to memorize pKa's? No, because to me, you're just going to memorize a number, and you could actually just hone in on the skill of predicting acidity without needing to know its pKa. Anyways, we should get back to it so we can wrap up class. One last type of organometallic for us to cover, and that is the organocuprates. These are sometimes called by a lot of different names. They're technically better called lithium diorganocuprates. Lithium is a cation, so of course it's always listed at the front of a name. And then you can see the abbreviation there is R2. So a better name than organocuprate is diorganocuprate. Although a lot of people often just refer to them as cuprates. And I think you can hear in the name cuprate, copper is there. In order to synthesize an organocuprate,
Is it CuLi?
CuLi, yep. R2CuLi. In order to prepare a cuprate, we must already have an organolithium reagent. We then introduced copper 1 iodide, CuI. I want you to remember that there are two oxidation states common for copper, copper plus and copper 2 plus, copper 1 and copper 2. One of the most common oxidation states is copper 2 plus. This is copper 1. The stoichiometry is often indicated as well. It's really awkward though, because a lot of times you synthesize the organolithium first, and you show one organohalide, 2 equivalents of lithium, produces 1 organolithium. But we obviously need 2 equivalences of the organic to make a cuprate, which means the equivalence of copper is often added as 0.5 to indicate that you need half the amount of copper as you do the organolithium.
Do we have to know that?
You know what? I won't take points off if you don't show the equivalence there. I do want you to focus on the equivalence with lithium. I think it's meaningful to say that the organolithiums are formed by 2 equivalences of lithium. The other way that you could write this is just to say 2 equivalences of RLi with 1 equivalence of copper iodide. Those are the same ratio. It's just that oftentimes you're showing 1 equivalence of the organolithium reagent, so you need half the equivalence of copper iodide. Either way, these form the same thing. And I'm going to show it 2 different ways for us. Yeah, I really don't like it. It actually makes a lot more sense when you look at it from this direction. I'm gonna show you the byproduct on the bottom because I think that's more meaningful. So one way that you can look at it is R2CuLi. The other way that you can look at it is that you have 2 R groups bonded to copper, and that's copper 1 plus. And both of these R groups have their partial negative character, which means copper is bonded to more than it should be. That gives it a negative charge. That's balanced by the lithium. What's the byproduct in this synthesis? It's a lot easier to predict the byproduct from the bottom reaction. The stoichiometry just looks better. Lithium is not in the byproduct. Oh, no, sorry, 1 lithium is. Yeah, there's 1 lithium that's here. The second lithium is in the byproduct.
Wait, that lithium is
The iodide.
with something? Or what?
This lithium, taken by the cuprate. The second lithium bonds to iodide. So we get a byproduct of lithium iodide.
Wait.
Yes, sir.
The first lithium, it's just floating, was it? It has to.
It's an ionic compound. It's balancing
Oh,
the negatively charged cuprate. So remember, you can show it as a condensed formula. And the way that we write it, CuLi, it informs you that you're balancing the copper charge and the lithium charge together. You can also draw it as this complex. There's another way that we can draw this, and I think this is meaningful for you guys to copy down because it's going to be a common thing that you see. We'll show one carbon to copper bond, and then we'll bisect that bond with the parentheses. We'll cut through the bond between carbon and copper, and then we put a subscript 2 underneath the parentheses, which is to say copper has 2 of these R groups bonding to it.
you put that copper has a negative charge, and then as it goes away, it has more negative. Is that right?
Yeah, I mean, I can see why it feels confusing. The copper has a negative charge, but the polarity is pointed towards the carbons. So the carbons hold the electrons. Why then is copper negatively charged? Well, this is not actually the first time you've seen this. This isn't as relevant, but if it helps explain the charge, this is good. We've used this reagent, sodium borohydride, before. Boron, this is BH4 minus. Boron has a formal negative charge. It is bonded more than it prefers to be bonded. But the dipoles actually point out towards all of the hydrogens. So the partial negative is on the hydrogens. The formal negative is on the boron. There's another place we've seen this much more recently. That's in the catalyst complex of our chlorination, alkylation, and acylation. Aluminum holds a formal negative charge, but all of these chlorine atoms are more electronegative. So the partial negatives are at the chlorines. Aluminum is just bonded more than it prefers to be. Copper is bonded more than it prefers to be. Being that it's a copper 1 ion, it likes to have one bond, ionic or covalent. But here, copper has 2 bonds. It has too much electron density, negative charge. The polarity points towards the carbons. Does that help explain it?
Yep.
All right. Let's do some examples then. And I'd like to take these examples a step further and then have us actually do some multi-step synthesis. Now, we're running out of time in class. We've only got 2 minutes. And I really think these syntheses might take you more than 2 minutes to do. So I might send you home with these syntheses. I want you to think about them. Brainstorm, at the very least, what reactions might be useful in these syntheses. And when we come in tomorrow, we'll start by solving these multi-step syntheses. And then we'll get back into reactions with alcohols and ethers. This will be, all of these reagents will be a very useful part of our synthesis. On your way out, I'll meet you at the door. I'd like to hear your muddiest point from today's class. What is the one thing that you think you need to go back and keep reviewing before tomorrow's class? All right.